Okay, good morning, everyone. So today we have another talk on super resolution. Last week, Onur has talked about image super resolution. And this week, Nasrin will talk about her recent work on video super resolution. Nasrin is a PhD student at Multimedia Vision Graphics Lab, working with Murat Hoca. And she is also a KUIS AI Center Fellow. The stage is yours, Nasrin.
Okay. Hello, everyone. I'm Nasrin Rahimi, and today I would like to talk about our recent work on learned perceptual video super resolution with natural texture and motion. Okay, let's get started. This is the outline of my presentation. I will start with the video super resolution, then I will introduce one of the state-of-the-art architecture on video super resolution and generally video restoration, which is eDVR, and the role of deformable convolution in eDVR. Then I will discuss a little the perception distortion trade-off and its necessity for video and image restoration tasks. Then I will present our work in 2 steps. First, the method to achieve a natural texture and then a natural motion. And after that, I will present the quantitative results and also we will have a conclusion. Okay, as we know, the single image super resolution or SISR, its aim is to upscale and enhance the images. We have one single image and we use the algorithms to hallucinate some details and high frequency information in it. Maybe you think that because of the data processing inequality, processing data cannot add information. For example, if the X is our high resolution image and it is degraded to Y, we cannot restore the Z to be to have higher mutual information than Y. But we should care that using the deep neural networks, the information is there inside the training data set, and using that, the deep neural network can hallucinate some details using the information that it's not in the Y or the degraded version. Now, in the case of the video super resolution, further than the data in the training set, actually, we have some good data in the sequence of the neighboring frames. Because of the redundancy in the neighboring frames in a video, we can use them. So all the video super resolution architectures use this idea, and there is 2 important steps to do this. First, the algorithm should align the features or the images to the original one. Let's say the middle frame is the reference frame, and we want to use a sequence of neighboring frames to super resolve this reference frame. So the first task is to align the features or the pixels to the reference one. And then the algorithm should fuse them properly and efficiently to provide a super resolved image frame. And also another issue in the case of video super resolution is that we should care about the consistency and the natural flow and motion of between the frames. This is another very crucial point. Okay, based on this, the eDVR, which is a video restoration with enhanced deformable convolution network, it's the winner of entire 19 video restoration and enhancement challenge. And it is a general task architecture which won all of the tasks, such as video super resolution, video deblurring, denoising, and other tasks. And here you see the full architecture. Actually, in the case of the video super resolution, because the data that they used was not blurry for the video super resolution, so they don't use this pre-deblur module. There are three important modules here: the Pcb Alignment Module, the TSA Fusion Module, and at the last, the Reconstruction Module. The important part here is the Pcb Alignment Module, which has the most contribution of the EDVR. Why it is very successful? Because it uses the deformable convolution inside it. I will talk about the PCD module, but before that, let's talk a little about the deformable convolution layer. Maybe you are familiar with this deformable convolution. In the traditional and normal convolution layer, we have kernels and their position are fixed, and every weight actually are applied to a fixed point in the receptive field of the kernel on the input feature map. But now the idea of the deformable convolution is to learn some offsets and then apply the weights of the kernel, the learned weights of the kernel, to the pixels far from the original. And this distance can be learned using these offsets. In this way, the deformable convolution is more general, and its capacity is more than the normal convolution layers, because it can use different invariants, such as, for example, you see here, it can learn the scaling, it can learn the rotation. Sorry, it's better. So it is more general and useful. And now the EDVR uses the REDS data set, in which actually there are complex and large motions. To align the frames back to the reference one, they use this deformable one, because using the normal convolution, it cannot cover large motions. So they use this one to handle the large and complex motions. And in this image, you also see how it works. Actually, using a convolution layer, it learns the offset fields, and then also it learns the weights, and then it applies the weights to the positions that the offset refers to on the input feature map. Okay. The PCD module, or Pyramid Cascading and Deformable Alignment Module, uses this deformable convolutions. Here, it also used a pyramid structure to align the features in a coarse-to-fine manner to handle, again, the large motions. And the structure is simple for each reference one, for each reference frame and its neighboring frames. First, the features are extracted, then they are concatenated, and using a nonlinear transformation, the offset is estimated. Then the offset and the feature of the neighboring frame is applied to the deformable convolution to create an aligned feature. And in each level, this repeats until we find the last alignment feature for every neighboring frame. Then they use the TSA, or Temporal and Spatial Attention Module, to fuse these aligned features. Actually, they find by dot production of the aligned features with the reference features, they find some temporal attention maps as you see here. And then they did an element-wise multiplication to find the best features. And then again, here in the pyramid structure, they find some spatial attention maps. And at the end, by mixing them and fusing them, they find the last aligned features. Okay, here you see the data set. The data set they used are introduced in the entire 19 challenge, and it is the realistic and diverse scene data set, or REDS. You see 2 samples of 5 consecutive frames here. As you see, it contains different kind of motions in it. And the training details for the EDVR, we use the version with 64 filters in each convolution layers, and also the TSA module. The batch size is 16, and the most important thing here is that their last function is the Carbonier penalty function, which you see it here. It is a pixel-wise, again, pixel-wise loss function, and it is a trade-off between the L1 and L2 loss based on their paper. And in this slide, you see the results of the EDVR. This image is from their paper. They compared the EDVR with different video super resolution network, as you see here. And you see that from this table also, you see that the EDVR performs the best in terms of the PSNR and also SSIM. Okay, but what's the problem with this EDVR? If you compare these 2 images, the left one is the ground rules, and this is the result of EDVR. Actually, if you compare, I don't know if it is clear on your screen or not.
I think Nasrin is frozen.
Yep, Nasrin.
Let's wait for a couple of seconds. Neslihan, maybe you can pause recording.
Do you have my screen now?
Yes.
Okay. Okay. I was telling that if you compare these results, you see that the EDVR is overly smooth. Yes. This is the drawback of the methods that use the pixel-wise loss functions. So this is not natural. So we can understand the PSNR, maximizing the PSNR is not a good measure to show the human vision perception quality. So a human, when looks at this result, quickly understand that this is a result of artificial algorithm and it's not natural. So the goal of the image and video restoration algorithms is not only to provide a similar super resolved image to the high resolution image, I mean to find low distortion or high PSNR, but also to find results with good perceptual quality. Okay, now our goal is to find a perception distortion trade-off using this EDVR. But what's the perception distortion trade-off, and what's the perception? What is distortion? To understand it better, you see here an image from this paper, the perception distortion trade-off. This is the original, let's say this is the original image, and using a degraded version, py given x, it is degraded to y, and using Px hat given y, which is our reconstruction model. We want to reconstruct this and estimate the x hat. So the x and x hat has their own distribution. Now the distortion is how similar the x hat to the x or the ground truth. To measure the distortion, they select a dissimilarity metric. Then they find the expectation over the joint distribution, and this is the distortion. For example, finding the MSE between the images, and this is a measure of the distortion. For the perceptual quality, for example, let's say we have some images, some are natural, some are fake, and we ask some human to judge between them if they are real or fake. If they both are real, the probability of success to distinguish between them actually is very low, okay? Because it is 50% by 50 and 50%. It is not distinguishable. And this probability of success in this test is proportional to the divergence between the two images distribution. So the perceptual quality is the degree to which the super resolved image looks like a natural image. And it is proportional to the human mean opinion score, as I explained here. And also, it is well known that the GAN loss functions, actually the GAN adversarial losses, is proportional somehow to the divergence between two classes. So we can use the GANs to add some perceptual quality to our results. And this is again from this paper that shows there is a trade-off between the perception and distortion, and algorithms cannot achieve both low distortion and good perceptual quality. As you see from this blue line, if an algorithm tries to decrease the distortion, I mean, moving from right to left, this is in the cost of increasing the, decreasing the perceptual quality, and vice versa. If an algorithm wants to increase the perceptual quality or come down, this is in the cost of increasing the distortion. So the purpose of the algorithms is to find the best trade-off in this perception distortion field. Okay, you see another image from that paper here. Actually, using the pixel-wise loss functions provide us a blurry and over-smoothed result because it provides the average of a lot of, all possible solutions. And using the GAN losses provide one of that natural actually solution. So the purpose of the perception distortion trade-off is to find the minimum divergence between the distributions such that the distortion metric is lower than some threshold. This is equivalent to select the generator loss as a combination of the distortion and adversarial loss in a GAN structure. So, for example, a SAR-GAN network used this idea and they created a GAN structure. Their generator is a super resolution network, and they used a CNN-based discriminator. For the generator, they use this kind of loss function, and then they train them, fine-tune them together to force the generator to provide more natural solutions. Okay, inspired by this work, we also, this is our first model, we train this model, we use again structure again. For generator, we use the EDVR I explained. And for the discriminator, very similar to the SRGAN, we use the CNN-based 12-layer CNN architecture with dense blocks at the end. We use this generator loss functions that has 3 terms. Again, the SRGAN use the combination of VGG loss and adversarial loss, and also the MSE loss. We used this idea too. And this is the loss function for the discriminator, as you see. I will show the weights that we selected at the end. But, okay, how we trained it? Actually, first we used the pre-trained EDVR model, the official one. And then we used it as a feed-forward network. We trained the discriminator for, let's say, 15K iterations. Then, using this loss function, then we put them together and train them or fine-tune them for, I think, 15K iterations again, using this generator loss function. And this is the result of our network. As you see, this is the EDVR and this is model number 1. Again, I'm not sure if you can distinguish between them on your screen, but again, the EDVR is overly smooth, but you see some texture and natural details on model 1 result. Okay, so far so good, but the problem with model 1, as I told at the beginning, the other crucial point in the video super resolution task, we should care about the temporal consistency and possible motion artifacts. When we was watching the videos, we understand that there is some motion artifacts in our model 1. And this is because of adding some hallucinated details and artificial texture in it. So it perturbs the flow and it causes some actually motion artifact. To show it better, we use the temporal profiles. What is a temporal profile? Actually, in, for example, 100 consecutive frames, we select a fixed line, and then we scan that fixed line in all of the frames and stick them together to find this temporal profile. This is the temporal profile for ground truth. This is the EDVR, and this is our model 1. If you compare them, you see that the model 1 is different, very different from ground truth in this part, and this part exactly are the part that we observed the motion artifacts. But to remedy this problem, we also use another discriminator, but this discriminator works in the flow domain, okay? So now we want a consistent flow, also a natural flow. To reach to this goal, we added another loss, the flow loss, that consists of 2 terms. One is the flow MSE loss, and the other is flow adversarial loss. Because just adding the flow MSE loss is not enough. Now, we don't want to force to learn the flow just similar to the ground truth image, because now our image is a little different from ground truth. It has some textures that maybe is not very similar to the ground truth. So we add these terms here. To calculate the flow, we use some optical flow estimation network. I use the PwC network. Then we calculated the flow between the ground truth frames and between the super resolved frames. And then we feed them to the discriminator, just like the pixel discriminator, which learns to discriminate between the real and fake images, or ground truth and super resolved images. Here, this discriminator tries to learn distinguish between the real and fake flows. Okay, and simultaneously, the generator is updated using this loss function, which has 5 terms, 3 for the pixel-wise losses and 2 for the flow-wise losses. Okay, and here you see the results. This is again EDVR model 1 and our model 2, the second model. You see again comparing to the EDVR, model 2 gain some realistic textures and is not smooth. And when we compare the motion for this model with model 1, you see that this problem of the motion here that caused the motion artifact is more better now and is more similar to the ground truth one. And this method actually improved the motion and removed the motion artifacts somehow. And here you see the quantitative evaluation results. This is on REDS4 dataset, which is 4 clips from the RED dataset we used as the test dataset, just similar to the EDVR. And this is the average results in bold. You see that the EDVR gains the best PSNR and SSIM because its loss function was pixel-wise, and this is natural. And model 1 and model 2, their PSNR and SSIM decreased, but their LPIPs, which shows the perceptual quality and naturalness of the texture of the frames, is again decreased, meaning that it is improved. Lower LPIPs is better. Okay, so comparing to the EDVR, model 1 and model 2 gain better LPIPs or perceptual quality, but lower PSNR or worse distortion. And this is completely okay because of the perception distortion trade-off we talked. One is in the cost of the other.
Nasrin, I have a question.
Yes, Hocam.
Can you come up with a numerical measure for the temporal profile? Because the best advantage actually of model 2 is in the temporal profile, but we don't have a numerical measure for temporal profile.
Yes, Hocam, I was thinking about that. Maybe we can find again the MSE of the temporal profiles.
Maybe, but you should think about that. I think we have to put a numerical measure here regarding the temporal profile also, because that's where model 2 is better and these numbers don't really show that very well.
Yes, Hocam, sure.
Okay,
sure. I will work on that.
Continue.
Also, you see the motion L2 loss. The motion L2 loss for EDVR is the best, again, because it doesn't have that perceptual stuff added to it. So it's comparing with the ground truth, it has the best motion L2 loss. But when we compare the model 1 and model 2, we see that in model 1, the motion L2 loss is increased, and this is because of the changing the flow. And using the MSE L2 loss, it is decreased a little. It is again obvious. Also, we use the VMAF, which is for Netflix, and it uses a combination of the distortion and perception and the temporal quality for videos. And you see that between model 1 and model 2, the model 2, although the LPIPS is not better than model 1, and also PSNR is the same, but the VMAP that uses the temporal consistency factor 2 is improved a little comparing to model 1. So to sum up, we can tell that using L2 flow loss and the texture and flow discriminators, it is possible to create a balance between the distortion, texture perception, and motion perception in video super resolution. Also, the desired distortion and texture motion perception trade-off can be achieved using the adjusting this weights, the 5 weights that we use for the generator loss function efficiently. Okay, that's it. Thank you for attention. And if you have any question.
Yeah, I just saw Fatma just typed something saying that she's using FVD, and I sent you a paper about FVD sometime. And can you tell us about FVD metric? Why we are not using it?
Hocam, I'm not sure. I didn't work on FVD.
I thought I sent you that paper. That was some French name. I remember. I don't know.
Yeah.
Personal something.
Yes,
like
I think it was in TensorFlow, as I remember.
Yeah.
Yes, but I didn't use it. Also, I have some
maybe
other
Fatma,
metrics such as
maybe
movie.
Fatma can tell us what's good about the FVD metric.
It's exactly what you said, Hocam. I think it measures the temporal consistency.
Really? Okay. So Nasrin,
basically, it is proposed for as an extension of the FID metric for computing the photorealism of the generated samples for the generative models, which includes like it computes the feature statistics, I think, using a 3D convolution based network, and just compare the distributions.
Yeah, Nasrin, maybe you can talk to Fatma and I could learn more about this FVD metric, and let's try that too.
Sure. Yeah.
Hocam. Sure. I remember that it was using for some generated videos using the GAN structures for video gaming or something like that. I remember this point. And I just thought maybe because our videos are very similar, very similar, and their difference is very subtle. So maybe it's not that much usable. Because of that, I didn't try it, but okay, I will try it.
Okay,
sure.
let's try and see what happens. And if not, you can use that mean square error of the temporal profile as a measure. We need another measure basically for better temporal consistency. Numerical, sure. I mean. Yeah, I mean, the temporal profile is nice. When you look at it, you see it, but there is no numerical metric right now that shows it. Okay, I'm done. Other questions?
So, Nasrin, can you go back to this architecture slide for the second model, where you introduced this flow-based discriminators?
This one?
Yeah, this one.
Okay.
So here, you basically compute the optic flow from the output of the generator, but you are not directly using the optical flows computed from the low resolution sequence. Am I right? So just I'm thinking about how you can just improve this. So basically you have also this coarse optical flow information that you can easily compute from the actual low resolution inputs.
Well, this is a good comment, because actually she has observed that there are some flow errors, also estimation errors. So we have some other model right now that she's working on. to compensate for that. But estimating the flow from the low resolution frames is a good idea. We should also try that. Yeah, what do you say, Nasrin?
Yes, hocam, we can try it.
You showed us this pyramid structure. Maybe you can also design this discriminator to have such kind of a pyramid structure, maybe.
Hocam, I didn't get your idea.
So basically, you can easily also compute the low resolution version of your generated output, and you can just enforce some consistency between the optical flows from the actual input and the low resolution of your output, like introducing some multi-scale.
Well, I mean, what he says is you can enforce the optical flow consistency at the low resolution space. So instead of estimating the flow from the generator output, you can downsample the generator output and estimate the flow there, and then make sure that the downsampled basically generator output's flow is consistent with the low resolution input flow. You see that, right?
Yes. Yes, hocam, but I'm not sure if it is it has advantage for our super resolved results. For example, here the low resolution images are obtained using the bicubic downsampling of the high resolution images. And if we downsample by exactly that method, I think they should be the same. No?
No, because I mean, one is the low resolution image, the other is your generator's output downscaled. It's not the same.
Oh, okay, okay. You mean I should downsample the super resolved image? Then,
yes.
Okay.
And then look at the flow of the downsampled super resolved images versus the original low resolution flow.
I got it. Okay,
I think that's a better idea. You should definitely try that. I think that's a good idea.
Okay, hocam.
Thanks, Aykut.
Thank you.
You're welcome. So one of the best working ideas in this generative adversarial networks is the introduction of the patch scan approach. Basically, it also introduces some kind of image pyramids to the discriminator that actually trains multiple discriminators at different scales. Maybe you can just think about how to form this pyramid structure in your problem. Yeah, it might help.
Okay.
You can try.
Thank you. Thank you very much, hocam.
Okay, any other questions, comments?
I would have a question, if it is okay. Sorry for that.
Yes, yes, sure.
Yeah. So thank you for the great presentation, first of all. So I also graduated from electrical engineering, but for my work, I'm doing some research on this super resolution imaging and I mean, converting videos to some sharp frames, so single images. So about this generative model, so this model that you have, would you please go to that slide if possible?
You mean this one?
Yes, yes. So I see that you use this TSA part. Did you try other ideas on this TSA, or you just used it? So what was the reason you choose this flow? I mean, starting from TSA. So the in the generation part, basically.
Okay, I used the complete EDVR architecture without changing anything in it. Actually, TSA fusion module contributes just, I can say 0.1 or 0.2 decibel PSNR for the EDVR, and it's not that much important. We can either keep it or remove it from our architecture, but I just arbitrarily tried to use a full architecture.
I see. Okay. Okay, thank you. I got the idea. Thank you.
You're welcome. Okay.
Okay, any other question? So
Nasrin,
maybe
I
I
have
can. Yeah, go ahead, Erkut.
quick question. So you only show LPIPS as the perceptual metric, but there are many other kinds of perceptual metrics. So why you stick with LPIPS and did not try the other ones?
Which one do you recommend?
So maybe I can. So in our study we use PyApp, for instance.
Okay, yeah.
Murat Hocam, and let me. So there is work on image quality assessment for perceptual image restoration in ECCV 2020, and they suggested a large-scale data set analyzed many different perceptual metrics. I think the problem with LPIPS is that since you are using these semantic features extracted with a convolutional neural network model, you in a way lose the spatial alignments. So they are shift invariant, so they cannot directly enforce the consistency as the standard pixel-wise losses. So maybe instead of using LPIPS, you may try other kinds of perceptual quality metrics in your loss function, and maybe you can extend your analysis. And I saw that in this year's entire challenge, there's an entire workshop, there's a new challenge on perceptual image quality assessment. So I think everyone now figured out that PCNR and SSIM like pixel-wise losses are not the good way to assess the quality of these studies. So let me.
Okay, well, I mean, I can say something in this perception distortion trade-off framework. They recommend that the perception metric should not directly be measuring fidelity. And the fidelity metric should not be really doing the perception thing. So they should be orthogonal to each other, kind of. Actually, the fact that LPIPS is not aligning pixels is kind of good in that sense, because the framework is based on the perception metric being orthogonal to fidelity. So I don't know if I can explain myself, but so there actually they don't even use a perception metric like LPIPS. They are using the KL divergence as a perception measure, just basically the PDF similarity. So I mean, that's why we prefer basically no reference kind of metric for the perception thing. And also, I mean, what we use in the loss function and what we use to actually measure the perceptual performance are not the same. So maybe we should also think about that. So she uses the VGG loss in the loss function of the network, but we use LPIPS to measure the performance. So that's kind of also. Anyway, so those are my thoughts. It's not really a good answer to your question, but those are my thoughts.
Yeah, thanks.
Nasrin, what do you think?
Yes, Hocam, we can try a bunch of perceptual quality metrics to see the results. Actually, because of the deadline, we just tried a few of them. I think it's better to test the other metrics, especially the non-reference one.
The general experience is that there is no one metric that is perfect, basically, for perceptual quality. So what's your experience with PyApp, Erkut?
So I shared a paper in the chat screen, Murat Hocam. So they, as I said, suggest a large-scale data set for perceptual quality assessment.
So do they recommend PyApp?
PIF was one of the metrics that are more correlated with the mean opinion score, as far as I see.
Okay. Okay. I'll check that paper. Nasrin, you can also check the paper.
Okay, John, sure.
Maybe I can ask one final question, but this will be more about the underlying approach that you are using. It uses these deformable convolutions. So in terms of the parameter counts, you are like maybe doubling the number of parameters. How was your experience with this framework? Like, did you need to make some modifications, especially in terms of the batch size and something like that?
You mean by deformable convolution?
Yeah.
The big problem with deformable convolution that I faced during the training the EDVR, although I used the pre-trained weights of the EDVR, the official one, but before that I tried to train the EDVR from the scratch, and one of the most important challenges that I faced because of this deformable convolution is that its offsets is not stable. The version that I use, because when the structure is very deep, after some iterations, the offsets, the mean of the offsets, for example, exceed 100, and in this 100 pixels, I mean, and in this way, it is not usable and it's not valid to use them. So even the EDVR authors also recommended to, when we face this error, to stop them and start again from a model that the offsets are okay. Again, when I was fine-tuning my models using these discriminators, after some iterations, I faced them. To remedy this, based on a paper, if I remember the name, we add another term to our generator loss function that penalties the large offsets, and it solved the problem. Yeah, it solved the problem.
It makes sense. Okay.
I don't
Thank
know
you.
if I answered your question properly or.
Well,
No, I was just curious.
he
Sorry,
asked,
Murat Hocam.
yeah, I could ask your batch size. What is your batch size?
For the EDVR, they use 16, but for fine tuning, I use 8.
8 frames? Yeah. 8 frames or
8 batch of frames. In each sample, I'm using 5 consecutive frames.
Okay, so that's 40 basically, 8 times 5.
Yeah.
Yeah, okay, good. Not 8, okay.
So maybe we can have one final question before we stop. Then I think that's it. Thank you, Nasrin. This was really a very interesting and inspiring talk.
Thank you very much for your attention and time.
And by the way, this is this work is submitted to ICEP 2021, so it's under review currently.
Okay, good luck then.
Thank you.